All right, thank you very much, Matthäus, for the introduction. Yes, so it's a great pleasure to be here today. I would like to thank the organizers for the opportunity to contribute to the conference. So, it's really quite amazing nowadays to see the level of complexity and subtlety that goes into doing cutting-edge graphics for video games. And I've been learning a lot new things watching the great talks here at the conference. In my presentation, we're going to do something a bit different because we're going to go back to the roots of graphics hardware. And so it's going to be about squeezing as many pixels out of very tiny hardware devices that we are going to design ourselves. What I mean by designing hardware, and hopefully this works, yes. What I mean by creating hardware is really doing hardware for real, right? The reason you can do this nowadays is thanks to open source initiatives, which have been around for quite some years, but now are coalescing into these great tool chains that you can actually use to describe hardware and also to implement hardware. So you can do that on FPGA. If you don't know what an FPGA is, don't worry, I'm going to explain in this talk. And you can also do that on actual silicon, creating your own application-specific integrated circuit, or ASIC. That means your own specialized hardware on a piece of silicon that you can solder on your board to create your own graphics device. So that's the real deal. We're talking about actual hardware here. So just to fix ideas, here is an example of an FPGA generating a test pattern, HDMI test pattern. And what's important to realize is, so the FPGA is in the middle of the board here. And an FPGA, when you buy it and you install it on the board, it does nothing, right? It's like unformed hardware. And it can shapeshift into any other hardware that you describe to it. It sounds a bit magical, perhaps, but you'll see that it's actually a very clever and elegant and simple process that I will describe later. What's also important to realize is you're alone on this board, right? There are a few peripherals, but here the video signal that is being generated is entirely implemented by the FPGA. So it computes the color of the pixels, it's generating the signal that goes directly into the wires of the HDMI, and you, the hardware designer, are responsible for everything that's happening on this chip. Right, so you're alone on your piece of hardware. Now you can do some more interesting things, like this 1080p Menger sponge fractal that is being remarched every pixel with 190 steps, and this is performed racing the beam. That means there's no frame buffer. In fact, the fractal is being generated in every pixel at the speed of the video signal without any memory. And this is only possible because you can design your own piece of hardware that does only one thing, which is that, but it does it very efficiently. If you try to do that on a modern CPU, it's actually quite hard to reach this kind of level of performance. It will require very serious optimization. Of course, your GPU will do it very easily, but that's not at all the same cost and watt per cycle ratios, right? So we are many orders of magnitude below a modern GPU in terms of that. All right, so hopefully you're intrigued. You might be thinking, oh, that's pretty cool. But why would I do that, right? I mean, what is the benefit of doing this kind of things? So a first reason is to get back the freedom to hack. What I mean by this is on modern computers, we have many, many layers of hardware and of software. So between the line of code you write that is supposed to be displaying something on screen and what happens on screen, this goes through a ton of different things that are very hard to decipher and fully understand. In fact, even the boot process of a modern computer is somewhat of a mystery, right? There are good reasons for that, of course. It's mainly due to security layers that avoid processes to pick and poke the memory of other processes. But it's also making computers very difficult to explain in terms of education to students because it seems like it's a very complicated affair. And in fact, a computer doesn't have to be complicated. If you're running bare metal and you're alone on your piece of hardware, yes, there are many, many things you can simplify, and you can go along with a simplified working computer that is still performing very well. And so I believe that for students, it's a great way to build a computer from the ground up and to implement your own software on your own hardware and really deeply, fundamentally understand what a computer is about, what a graphics card is about, and what's truly happening on your computer. It doesn't have to be complicated or inaccessible. The other reason is a performance mindset, right? So now we have gigabytes of memory, gigahertz of performance, tens of thousands of cores on modern GPUs. It's really quite hard to understand, even for experts, I believe, the amount of performance we have at our disposal. And of course, it's fantastic to have this performance, but the problem is, how do you get into the mindset of properly using it when you almost never reach the boundary? So of course, I realize most of you in the room are deep into optimizing things for GPU, so you are reaching these boundaries. But for newcomers, for people entering the field, whatever they do, it's going to run fast anyway, right? So I think it's great to put yourself back in a context where you're creating your own piece of hardware, your own piece of software under very constrained resources, and you are constantly trying to optimize and to make things fast, and this puts you in the right mindset to keep doing that even when you're a platform where you're far from the actual constraints and limits, so that you can keep writing efficient things. And also, it's a great way to experiment out of the box, right? I mean, what if instead of triangles, we were using ellipses like the X-Tactica game from the 90s, right? What would it mean for your hardware? Well, you can experiment with that, and you can do real hardware that truly executes the design you imagined, and you can make actual measurements and actual comparisons on it. You can, of course, do that also in simulation. It doesn't have to be on a real board, but I would argue it's much more fun if it's actually running in true hardware. All right, so let's start our journey. I will proceed in 3 different parts. So first, we'll see how you do your hardware, your actual hardware in practice. How does it work? Then we'll do some Demoscene graphics at the micron scale, literally. And then we're going to go back to the future and imagine what would be a GPU for 1993 if we were to travel back in time with an FPGA in our pocket. So let's start making our own hardware. So of course, when you want to create hardware, you first need to describe it. And the way we describe hardware is by writing code. So in graphics, we're quite used to this idea that you can write codes that generates things. In particular, we do procedural generation of 3D models, for instance, where you write pieces of code that describes how to combine different volumes together to get a final object, right? So that's one example of code that creates something. Here, it's exactly the same. It's just the code you write as a side effect is describing a piece of logic that can be turned into an actual piece of hardware. So to fix ideas, let's look at a very simple line of code, which is C equals A plus B. And here we're going to say that A is a 1-bit integer and B is a 1-bit integer. And because we're summing them up, we'll get a 2-bit integer if we want to keep the carry around, right? And this little line of code can be turned into the following circuit, which is just taking the A and B wires as input and is outputting the 2 wires of C. So C0, C1, least significant and most significant bits. And it's using 2 gates, a XOR gate and a AND gate. And this is the truth table that corresponds to the sum of both these integers, right? So of course, in reality, when you build this circuit, the wires will get a signal inside that is not 0 and 1, but that is ground and VCC, typically 0 volt and 3.3 volts. And in an ideal world, they only take these 2 values. Now, because this is a physical device you're fabricating at the end, this is not as ideal as this, and in fact, things will take time to transition when you change the value from 0 to 1 or 1 to 0. And of course, there will be a little propagation time through the gates so that the circuit actually stabilizes into the final values. So there is a notion of a propagation delay through the gates and of transitioning between these signals. This will become important later in the discussion. All right, so such a circuit is called a combinational circuit because you have created a combination of gates to describe your computation. And of course, there are many other type of operations that you can describe as combinational circuits. So you have the addition, the multiplication, the shifts, and also the multiplexer, which is depending on the value of a condition bit t, you're going to select between A or B. And of course, all these different operations will lead to different types of circuits. Some will be smaller than others. So here I sorted them in rough order of complexity in terms of the number of gates they're using. And of course, this number of gates will turn into a different size in the floor print of your circuit, right? Because things take space. You're in the physical world now. And another thing that is important is because of the delays I was describing in the gates, the more gates you have in the path, the more delays you will get, and these delays will limit the maximum frequency you can reach, and I will come back to that later on. Okay, another important thing is when you write an if statement like that, if C, A, else B, there's no notion of not doing something, right? So in a CPU, typically you can hope that if you take the branch, the other branch is not getting executed. Of course, on the GPU in lockstep, we also have similar issues where both sides are going to be executed and only one is selected. And this is what happens here, because here you have to build the circuit A, you have to build the circuit B, and they will always exist. And the condition is only choosing one output versus the other, right? So sometimes it's more efficient to not try to be subtle, to not try to place a condition if it's never hit, such that you don't create unnecessary circuitry. Okay, so now we have gates, but we need something else that is very important to be able to build hardware. To understand this, I'm going to build a very simple circuit, which is implementing A equals A plus 1. Okay, so I have an adder, let's say it's 8 bits, so I have 8 wires for the signal A, and I'm computing A plus 1. I will loop back the output of the circuit to its input. That's how I implement A equals A plus 1. There's nothing wrong with that in terms of the physical circuit. It's not going to blow up or melt down. But it's not going to do exactly what you want. And the problem here is that the circuit will be free running, and as soon as the output is updated, the input is changing, the circuit tries to update as quickly as possible the output, and this goes on and on. And the problem that is even worse here is that you have several wires that go through different paths in the combinational circuit, so they don't have the same delays. So things will completely sync out, and what you get out of the circuit is actually mostly random. Right? So what I've just built is called a combination loop, and this is a bad thing, right? Normally, apart from very specific rare cases, you never want to build such a combinational loop. So you need something else, and what you need is synchronization to make this work. All right, so to do synchronization, we are introducing a new component, which is called a flip-flop, and we're going to insert the flip-flop on the output of the adder, and then loop back the output of the flip-flop to the input. So let's assume, for the sake of the example, that on these wires, we have bits that are creating the number 131. Right? So of course, the adder will output 132, but the flip-flop right now will do nothing. It does not copy the output. It's memorizing the previous output and will not change it until a very specific event occurs, which in this case will be the positive edge of the clock signal. It could be the negative edge as well. This is configurable. When the positive edge occurs, then it copies the input to the output. And of course, this goes back to the adder, which immediately refreshes the output after a tiny delay that I've shown here by moving the clock a little bit. But this delay is much shorter than the clock frequency, hopefully. The flip-flop keeps this value until the next top. And as it does this, the circuit is now stable. And at the next clock cycle, it will properly update the value, and this process will continue, and you will get A equals A plus 1, where the value is updated every clock cycle. Right? So that's how you introduce synchronization in a circuit, so that you can do well-defined hardware. That's one of the big reasons we have a clock in our designs. All right, so we have gate and flip-flop, so let's see the whole process to go from code to an actual design in hardware. So this all starts from the code you write using a hardware description language, or HDL. I'm going to show you a few snippets of codes in my own HDL, which is called Silis, but you might have heard of Verilog and VHDL, which are also like the most standard HDLs. So you're running this code through a process that is called synthesis. And the reason it's called synthesis is because the tool is trying to identify some of the constructs you have in your code and map that into known pieces of hardware, multipliers, adders, memories, all sorts of different things. What the tool outputs is a graph of gates and connections, networks between these different gates, right? So it's a graph with general edges because you can have fan-out, so you can have the output of one gate connected to the inputs of many other gates. One very nice tool to do that, a very powerful tool, is Yosys. This is open source, and so you can use it for all sorts of different hardware to generate these graphs. Now, given this graph, you will enter a process known as place and route that will now create a physical blueprint of your hardware by mapping the graph onto hardware primitives and creating wires between them. And the output will be different whether you target an FPGA or an ASIC. And I will discuss that in a minute. The tool to do that on FPGA, the open source tool, is called Next PNR, PNR being place and route. All right, so let's have a deeper look at how this works and understand first for FPGAs. I really like this die picture of the very first FPGA. This was in 1985. And when you look at this die picture, it looks like a bad texturing thing, right? Because you see a lot of repetition. And that's because, indeed, an FPGA is a grid of repeating elements. And if we look at these repeating elements, Well, so first, they're all alive in parallel. So an FPGA is like your ultimate parallel machine, right? Everything happens in parallel. All these cells receive the clock, the reset, and they are all alive, so to speak, together. If we zoom in on one of these cells, it contains two things. One of the things I've already talked about, this is a flip-flop, and the flip-flop is on the Q output. And then it contains a lookup table. So a lookup table is what makes the FPGA configurable. That's one of the two components to allow it to shapeshift into a different piece of hardware. So let me explain this. I'm going to remove two of the inputs so that it's a bit simpler. And the lookup table, as its name indicates, is simply a lookup into a table from the input values to know what should be the output value given the inputs. And by changing the configuration of the table, you can implement different types of gates. So for instance, XOR, OR, AND, or NAND. Right? So this makes the cell very flexible because it can become any gate you can describe by simply updating the lookup table. So it means there's a tiny bit of memory in each of these thousands or tens of thousands or hundreds of thousands of cells that compose the FPGA. Each have a tiny bit of memory that you can configure to turn them into any type of logical gate you want. All right, and of course, now these gates are in this very big grid. And first, some of the gates are connected to the outside, to the pins of the chip, the actual physical pins. That's how you have inputs and outputs. And then they have an interconnect between them. So that's a set of predefined routes between the cells. And in between the routes, you have switch boxes that you can also configure to create routes between the cells. That's how you're describing the wires of the circuits you're trying to do. All right, and so now that you can configure both the gates and the wiring, you can implement your own hardware on the FPGA, and the FPGA truly runs and becomes this piece of hardware that you have described, of course with some overheads, because it takes time to do this lookup in each of the cells. It also takes time to go through the switch boxes, so the delays are much bigger than what you would get on an ASIC. It's also taking a lot more space for what it does because of all the configuration and all the memory that is inside for enabling this configuration. One interesting thing to look at when you look at a route like that in the FPGA is the critical path. This is the slowest route through the combinational cells of the FPGA. So the Q output here is a flip-flop at the top left. And the D outputs are the combinational output of the lookup table. So they update as quickly as they can. And you can see that the last pin over there is also on the output of a flip-flop. So now what happens is that when the value changes at the top, the change has to propagate through the chain until it reaches the last gate, and it better reach the last gate before the next clock edge, because if it doesn't, we're going to register the wrong value. And this delay is actually what drives the maximum frequency of your hardware. Of course, it changes with temperature, it changes with all sorts of parameters, which makes you wonder what kind of guarantees do you exactly get, right? But the vendor tools will actually tell you for different corners of configuration, so essentially the temperature and the quality of your FPGA, what kind of frequency you can hope to safely reach. With some margin, so you can also try to overclock a little bit. But you can really quickly get into trouble. In principle, the FPGA can be configured to take any frequency almost. It can go much faster than the propagation delays that would be reasonable, so you really have to watch out for that. So it's not like you decide on the frequency. It's more like you do something and it tells you what frequency you can hope to reach. All right, so this was for an FPGA, and now just a quick note on ASIC. If you want to do this on an actual piece of silicon, well, it's the same. You have to go through a different toolchain. Yosis is still here, but the rest of the toolchain is different. And it will output a blueprint for your chip that you can send to a fab so that you get your actual piece of silicon, right? And this is a 3D representation of the different layers of a chip. You can see that there are some empty parts because my design is not using the full space available, which is, probably means I should have squeezed more features in there. And it's a color-coded view of all the layers that are going to be manufactured by photolithography onto the actual piece of silicon. And the top layers are wiring, for instance, on top of the gates. So you might be wondering, okay, great, I have this, but now how can I fabricate my actual chip, right? It's not like it's easy and you can knock on a door. Well, in fact, thanks to a project called Tiny Tapeout, which is an open source initiative, you can actually do that. You can buy a small piece of area on a chip that is shared between many users. So you can it's a crowdsourcing project for chip manufacturing. And so for around $100, a bit more if you need more space, you can rent this space on the chip. The chip is going to be manufactured, sent out to everybody who designed a piece of hardware, and then you have pins to select which of the designs you want to be using, and so you have to select your design, and then you can run it. And so it's a very nice way to get your actual chip manufactured, and this is running right now, and you can send your own designs. I will talk about it again in a minute. All right, so we've seen how it's possible to make our own hardware, so now let's have fun and try to do something. So first, we're going to do some Demoscene effects at the micron scale using tiny tape-out. In fact, the tiny tape-out team launched a Demoscene competition. It closed recently. This was back in September. The deadline was back in September. And the idea was to make a demo in exactly 2 tiles. Right? So 2 tiles is roughly 3,000 gates. And by gates, I mean AND, OR, XOR, and so on. So a gate is actually simpler than the lookup tables, because the lookup tables I showed you, normally they have at least 4 inputs, so they represent many gates. So here it's really, really small. Yes, by the way, this is the amount, roughly, of gates. Even if I'm off by 1 order of magnitude, you can see the RTX 4090 has a bit more gates than what we're trying to do here. So that's not a lot of space. And even though we can use gates to create memory, there's just no way you can fit a frame buffer, let alone a row of pixels in 3,000 gates. So that means we'll have to generate the video signal and the colors of the pixels at the same time for a display on screen. And what's more is that you have only 2 bits per pixel, so you better work on these dithering skills. And you have only 1 bit sample audio. So that sounds like it shouldn't be possible to do anything, but with pulse width modulation, PWM, you can actually generate very decent audio with only 1 pin output. Okay, there will be audio in my demo, but I have to warn you, I'm no musician, so it's going to be what it is, right? All right, so you can think of it, racing the beam, as a shader-style type of mindset, because you're given a pixel coordinate and you have to quickly generate a color. It's just that it's a bit more convenient because the pixels are generated in a specific order, so you can try to exploit this. Yes, so a few disclaimers. I'm going to show you the demo I made, but the results are not out. The chip is being fabbed. It takes roughly 7 months, so it's a long time. And so I'm not even sure my demo actually works in real hardware, right? I'm of course hoping so. And also there are many other great demos, so if you're interested, definitely check it out when it's gonna be released online. Here is my entry. There will be sound. Yeah, I'm not gonna put the sound very loud because it's just to convince you that yes, there is sound somewhere. So it's a mind-blowing 640 by 480. You can see there's an RGB shift, which is made on purpose. There's a lot of dithering going on to create the grayscale levels. And yes, and it generates, hopefully, interesting effects. So that's a hardware take on the classical tunnel effect. I think some of you probably recognize it. It was a very popular effect in the 90s. And the reason I chose this effect is because it typically uses a pre-computed mapping table. This is basically texture mapping, right? In every pixel, you have a UV coordinate, you look up your texture, and then you move it around in the texture space so that you create a nice tunnel effect. The problem is that this table is very big, right? In terms of our design, it's absolutely huge, and there's just no way we can fit this table. That's why I thought it would be an interesting use case for hardware design. So the goal is to compute this UV per pixel such that we have the illusion of a texture map, and you can probably recognize a XOR pattern between the coordinates creating this texture map, so it's also a procedural texture, of course. And the UV is computed from a circular parameterization. So what this means is you have a given pixel coordinate, you're creating a vector from the center, and you need to compute the angle of this vector and the length of this vector. Right, circular parameterization, and then, and for that, sorry, you can use the Cordic algorithm. It's a super nice algorithm to do trigonometry in hardware using fixed point integers. There's a very nice Wikipedia page about it, and you can compute both the arctangent and the length at the same time using it. So that's fine. And the other thing is that we have to do a per pixel division by the length to create the perspective effect. Right? And of course, the per pixel division is also a problem because the divisions algorithms are either iterative or they use a ton of gates and a ton of chip area. So give or take, this is roughly 20 iterations. This means I would need 20 clock cycles to generate the value of 1 pixel. But I don't have this luxury, right? Because I want to raise the beam, I want the full resolution, I don't want to divide the resolution by 20. I'm already running only at 640 by 480. I could try to use a clock frequency which is 20 times that, but I felt this was maybe pushing it a bit too much, even though in ASIC you can get to higher frequencies. So something else is needed. And if I can get to higher frequency, I prefer to have a higher resolution, right, and to not lose my nice resolution. So how can you do this? Well, because you are designing your own hardware, you can just unroll the iterations in a pipeline. And if you're wondering how this works, or you're not familiar with the notion of hardware pipelines, let me give you a quick explanation. So here we have 4 pixels on screen, A, B, C, D, and we need to make it so that every clock cycle we get the value of one of those pixels, so that as we generate the video signal which has the same clock frequency, we want the color of every pixel to come at every clock cycle. Here I'm going to show it for 3 iterations instead of 20, so I have only 3 stages, but I would have 20 for my 20 iterations otherwise. So at the first clock cycle, time goes from left to right. At the first clock cycle, pixel A is entering the first iteration. Next clock cycle, A moves to the second iteration, B enters the first iteration. Next clock cycle, A is at the last iteration, B at the second one, C is entering the first iteration. And next clock cycle, A gets out of the pipeline just in time for me to put it in the video signal. And from this point on, I get 1 pixel out of the pipeline every clock cycle, right? And of course, each pipeline stage is a different piece of circuitry into the chip, and they pipe into each other, hence the pipeline name. All right? Of course, there's one problem here, which is this latency as a start, right? Because you have to wait for the first pixel to happen. But the thing is, in all video signals, VGA, HDMI, and so on, there is a vertical blanking interval. That's because your electron beam had to go back to the top of the screen, and this blanking interval is still here. And it's a very significant amount of time in terms of clock cycles, so we can easily hide the entire latency inside this blanking interval. And yes, that's it. You're racing the beam at the resolution you chose, getting 1 pixel every time out of the pipeline. Now, let's look at how you instantiate that in terms of code. So this is, in my language, CDIS, where one of my goals was to simplify writing pipelines. So here you can see the arrows which are saying enter the next pipeline stage, right? And it will automatically do the piping of the variables throughout the different stages. Now you can also see a little bit of preprocessor here, which is repeating these stages, so unrolling the loop so that it creates the entire pipeline with all the iterations you want, and so you can very easily configure the number of iterations in the, the number of stages in the pipeline. By the way, this here is 1 iteration of the Cordic algorithm, so you can see it's very, very simple. It's doing a vector rotation to get the vector back to 0 while counting the angle. And when the vector is back to angle 0, the x-coordinate is the actual length of the vector. Right? That's a very neat approach. Okay, here is the chip that gets out of this. It's indeed fitting in 161 by 225 microns, so very small. It's at 95% density. That's quite high. Normally, you don't push it that far. You stay within like 70 to 80%, because that's the density of the gates, and my understanding is that the routing has to go around and above this thing, so when you are too dense, it might not succeed in routing. I believe the reason it works here is because it's a pipeline, and basically your input is a clock, and the output is a VGA signal, so it can fold this pipeline within the circuitry here. I believe this is what's happening, and the reason we can reach this density. It's 3,342 logic cells, and 65 millimeters of wires, which is enormous given the size of the chip. It's always quite amazing to think about how this is like, folding this thing inside. Beyond the algorithm I showed you, it also has the VGA signal generator and the audio. And don't worry, I don't know where they are either, right? That's widows. All right, so at this stage, you might be wondering, how do you go testing these things, right? Because if you have to wait 7 months for your chip, how do you even know it's computing the right thing? In fact, how did I even produce the images I was showing you before? Well, there's a number of great tools to help you out here. So first, there's Verilator, which is an open source tool that will take your hardware description and turn it into C++ code you can run. And of course, because it's C++, you can add your own library, and I made a library that will decode the VGA signal and show it to you as an image, and also can record the audio so that you can listen to the music you tried to compose, in my case. And so that's very fast, but that's quite far from the actual hardware, right? So you might not spot some other issues. Then you can also run gate-level simulation. It's the same, but you take the output of your sys, the graph of gates, and you take a simulation model of each of the gates, and you run simulation on that so that you have a much more accurate, even though much slower simulation. This also takes into account other states of your wires, so there's 0, 1, but there's also high impedance, like the wire is disconnected, and there's also an X state, which is unknown, because when you start up some hardware, if you don't do anything special with a reset signal, you don't know the values on the wires. And then you can run on FPGA, which is what I did with this particular design. You're very close to the hardware because that's actual hardware you're running. It has some gotchas because the FPGA will initialize wires to 0 normally, or to some value you specify, which is not happening in hardware, and I actually got bitten by this in one of my designs. And then you can try on the chip. This is what I hope to be receiving at some point, which is the chip on an ASIC carrier, and then you plug it into a special PCB, and hopefully it works. We'll see. So please join the fun. This is a very active community. It's very welcoming to beginners, lots of enthusiasm, and very talented people, so I highly encourage you to get started. I have a GitHub repo with series templates that has a VGA output, so that you can get started hopefully easily. And please let me know if you're interested and join the Discord as well. All right, so that's it for the demo scene at the micron scale. Let's now go back to the future and reinvent the GPU, imagining we have an FPGA in our pocket. So how does it started? I was working on my hardware description language, and I was trying to make the point that you can fit relatively complex algorithms into your hardware. So you don't really need a CPU or anything anymore. You can just take the algorithm and turn it into an hardware that does only that. And my example for this was, of course, Doom. And so I created what I call the Doom chip, which does only one thing, which is running Doom, until it's losing power. It's, in fact, not the entire game. It's the random loop of Doom. You can also open doors and turn switches and so on. But yeah, so it's quite nice in showing this is possible, but it's also quite brute force, right? It's using 25,000 logic elements, which is a lot, right? So after that, I tried a more subtle approach, which is the Doom chip on ice. And here, I constrained the hardware budget to be only 5,000 logical elements. So that's a small FPGA that I will describe later. And inside these 5,000 logical elements, I fit both a CPU, which is a RISC-V, like the simplest form of RISC-V CPU, as well as a custom GPU, so that it can accelerate rendering. And this is what you see at the bottom right. If you're wondering where the actual FPGA board is, it's fully embedded into the USB port, because the board is extremely small and disappears inside the USB port when you plug it. It's called the FOMU. And so you can see that, yes, you can fit Doom inside the USB port. Actually, I have another demo with Quake running in the USB port on the same device. Again, it's only the random loop. It's not the full game. All right, so I'm going to describe this in a bit more details because I think it's a good example of squeezing pixels out of a small hardware device and exploring how you can create your own hardware with completely different trade-offs than what is usually made. And these trade-offs appear from the constraints. So when you want to do something like that, first, I think it's good to fix your hardware budget before talking about target features. And for the hardware, I chose to use the ICE40 UP5K FPGA. It's a FPGA that is very popular in the hobbyist community. The reason being that it's a very nice sweet spot in terms of cost. It's only a few dollars, and the features it provides, which is 5,000 logical elements, but also 8 DSPs. So the DSPs are hardware multipliers which are distributed inside the FPGA fabric, inside the grid of the FPGA. And the synthesis tool, Yosis, will know how to map multipliers to these hardware blocks so that you don't use your logical elements to implement multiplication, and you get very fast multiplications in these blocks. So there are 16 bits multipliers with a 32-bit accumulator, which means you can do multiplies and add. And for us in graphics, this is perfect. You have 8 of them. You have 15 kilobytes of VRAM. VRAM is similarly some memory that is embedded into the FPGA fabric. And this memory is extremely fast. You can read and write in a single cycle. Extremely convenient, right? External memory is so much more painful. So here it's read and write in a single cycle. Think of it as L1 cache type of memory. And you can also initialize it with specific values, which makes it very convenient. It's also very flexible in the size and bit width and addressing that you want. Very specific to this FPGA, it also comes with 128 kilobytes, such a luxury, of memory that is less flexible than the DRAM, but is equally fast. So it's also read and write in a single cycle, but it's less flexible in the way you configure the addressing and everything, and it cannot be initialized. And finally, we're going to target 25 megahertz, so that's one downside of this particular FPGA. The fabric of the FPGA is not very fast. The delays in the gates and switch boxes and so on are quite significant. So reaching 25 megahertz is already a very good target for this FPGA. Of course, we can go faster, but it's becoming very, very difficult. All right, so now what kind of features do we want to have on this small thing? Well, I want perspective correct texturing, right? Because I'm not buying any of this PlayStation texture swimming, right? I want very nice textures. I want a voxel terrain rendering in the manner of Comanche 1992. If you don't know the effects, I'm gonna show it later on. It's not truly voxels, it surely looks like it. I want light maps, because Quake. And I want a depth buffer, because this is 2024. We've figured out that sorting the triangles on the CPU is not great, so it's better if you can avoid it. So let's have a depth buffer in there. So yes, so now if you look at the target and the budget, it's, oh yeah, of course, sorry. We want the best resolution known to mankind, which is 320 by 200 pixels, of course, right? Indexed palette. So yes, so these features are a bit tricky, right? Because perspective correct texturing requires a division per pixel. It also requires texture memory. Your textures have to be somewhere. And light maps and depth buffer are using a ton of memory in terms of size, but also in terms of bandwidth, because you have to look up these depth values. And typically you need, let's say, 24 or 32 bits depth values to make something that works properly. 32 bits is quite nice. And the problem is that's the only significant amount of memory we have on this particular FPGA. So fitting all of that into 120 kilobytes is going to prove very challenging, keeping in mind that the CPU also needs RAM, right? Because the CPU is on the same FPGA. So how exactly are we going to solve this? Well, here is the FPGA architecture. The first thing to note that's going to be a big help for us is that the FPGA that is hosting both the CPU and the GPU is attached to a flash memory. And you can see it here on this icebreaker board, very nice board for getting started. This is the FPGA and this is the flash. The reason there's a flash is because this is where the FPGA is reading its configuration from when you boot up, when you power up the board, right? The FPGA has to be configured. This configuration is a file, so to speak, a piece of memory that is stored on this flash chip. A flash memory is very slow to write to, as in seconds slow, but you can read from it quite fast. In fact, you can reach 25 megabytes per second or even 50 megabytes per second from this FPGA. I managed only 25 megabytes per second so far. But others have done it at 50 megabytes per second. So I'm going to put the textures into this piece of flash because we don't want to do render targets. So that's a great place to upload your texture pack, and then you can access the textures when you do texture mapping. And this is going to use a very fast memory controller optimized for random access, which means I have bindless texturing because every text cell can jump around in memory, and in 9 cycles, I get the next text cell value. All right, in the SPRAM, the 128 kilobytes of memory, I'm going to put the entire CPU RAM. OK, great so far. But then where's the frame buffer? Right? And the frame buffer, I need to be able to write to it, of course. Well, there's a trick here. This design is attached to a small LCD screen, and this type of screens actually come up with a driver, and the driver actually has a frame buffer memory. So as long as we can stream the columns in order for efficiency left to right, let's say, to the screen, we don't even need to have a frame buffer because it's going to be on the screen itself. However, it means we have to rasterize the columns in order. All right, so that's fine for the frame buffer. How about the depth buffer and the light map? Well, from this constraint of sending the columns in order one by one, we can actually do the depth buffer and light maps now for very little memory because we're rendering screen columns one by one. So I only need a 1-column depth buffer and a 1-column light buffer. So I'm rasterizing this 1 column, sending it to the screen, which takes some time. Meanwhile, I can rasterize the next column, and I can proceed this way and send the columns to the screen in this manner. So I have a very nice 32 bits depth buffer and an 8 bits light map attached to my columns. almost for free. We'll see that, of course, there are some significant drawbacks to this. And yes, and this fits very easily in the 15 kilobytes of VRAM of the chip. So here is an example of Quake being rendered on this particular design. It's quite slow, right? It's like 5 frames per second or something, but you can see here the breakout between albedo and light maps. So for the light maps, what happens is I'm rasterizing again the same vertical spans, but switching the texture to be using the light map instead of the albedo, and this is writing to the light map part of the columns instead of the color part. And at the end, there's a mixing stage before sending to the screen so that we can shade the pixels. All right, significant drawbacks. First one, and I'm sure many of you have thought of it, right? Normally when you rasterize, you take a triangle, you rasterize the spans, of course here these are vertical spans, you forget about the triangle, you go to the next triangle, you rasterize it, and so on and so forth. I cannot do that because I have to rasterize the screen in order, column per column, and that's quite a disaster for some of the rendering engines. So with Doom, it's not so much a problem, because it's mostly a recaster in a map that is two-dimensional as seen from above, so you can get around this. With Quake, which is an actual rasterizer, no such luck, and the problem is then the CPU is really overloaded with trying to do this rasterization, and our CPU is not very powerful because there's no space to make a nice CPU in there, so it's only doing one instruction every 3 or 4 cycles, and it has no cache, and so on, so it's not great. So yeah, big drawback. Second drawback, because I don't have a frame buffer, I cannot create a VGA or HDMI output at all, right? Because to do that, you need to generate the video signal. As we've seen, you need to have the color of the pixels as you generate the video signal. And usually, you would pull them out from video memory for some form of fast VRAM, such that you have the data available, and I cannot do that. There's no place where this data is actually stored. And the third drawback, which is maybe the worst one, is that the CPU is too restricted, no pipeline, no cache, limited RAM, so I cannot run the entire game of Doom or Quake or anything on it because it simply wouldn't fit. Already to fit Quake, I had to stream the level data from the flash into the RAM to make it work, and so doing the full game, a part of the full game would be too hard. All right, so I thought maybe I was a bit too hard on myself in terms of hardware constraints, so I'm going to relax things a little bit to do another iteration, this time with a dual FPGA. And now I'm moving towards a more traditional setup where I have one FPGA for the CPU and one FPGA for the GPU. And thanks to this, I can now have a very decent CPU, which is pipelined, as a cache, as branch prediction, and is able to reach 1 instruction per cycle at my 25 megahertz, which is pretty good. Also note that I attached a second chip here at the top, which is similar to a flash chip, but can be written to very efficiently. It's called a QSRAM. So the Q is for QSPI, which is the protocol with which you communicate, and Q because it's a quad SPI, so you get half a byte every cycle in and out. All right, and the GPU has a similar chip attached to it. So let's look a little bit, the CPU is using the SPRAM for the cache, so 128 kilobytes of cache, which is really nice for instructions and data. And the GPU now is using the SPRAM for the frame buffer. 128 kilobytes fits exactly 2 320 by 200 pixels frames. So it was meant for it, right? It's just exactly the size we need. And here, let's talk a little bit about what happens between the CPU and the GPU. So of course, there are commands being sent between them. And the commands in my GPU design are 64 bits. And what they contain is the texture ID, the start coordinate on the column, the end coordinate on the column, the light level, the U and V texture coordinates start, and the V increment as you go down. This is for a vertical span, let's say, of a vertical wall. Of course, if it's a planar span for any plane in space, you have additional information that you send ahead of time regarding the plane equation. I have a full write-up on this that was linked before, if you're interested. However, the first drawback still applies, and the reason it still applies is because of the depth buffer. I still cannot have a full complete depth buffer. There would be memory size outside, but the bandwidth is really tricky to deal with. So I want to keep my per column depth buffer, but I need to solve this issue. It's too big of a problem. And so to do that, we can change things a little bit, and instead of the GPU consuming the commands as they come, we can just have the GPU write them in a scratchpad. And when they're all in, then it will process the commands in the right order. And the idea is, in most cases, you can hope that the number of commands, the number of spans to draw, is going to be much smaller than the amount of pixels on screen. Please don't do micro triangles, thank you. And that should work okay, right? So the access can also admit some latency, because when the GPU receives a command from the GPU, it's in no hurry to write it somewhere, and as it reads the next command, it can be drawing the previous one, so we don't have to worry too much about memory latency for the commands themselves. So here is how it looks when you're rendering a frame in this new design. So the CPU will send draw commands in any order. On the GPU side, we are filling in the per column command buffer in the order the spans arrive. We do nothing but writing this, so it's purely bookkeeping at this stage. And then the CPU is requesting a frame with a special command, and then the GPU gets busy and starts consuming this buffer in the order of the columns, rasterizing on screen. It will take some time, after which the GPU will signal that the frame is done. Meanwhile, the CPU is busy doing other things, and when it's ready, it will enter a waiting loop, waiting for the frame to be done. Here, it happens that we are CPU bound, so the frame will be done before the CPU needs to wait. Of course, it could be the other way around. Yes, and this is working quite nice. Here is the final design. You can see the one wire that is a frame-done signal that has to exist between them, and this is really how it's instantiated in the actual hardware. So with that, let me introduce the ICE Dual computer. This is just a code name. And here it is. And so this thing here has the two FPGAs in the back. Yes, so CPU plus GPU, it has some audio, VGA output is on the back, serial over USB, PS2 keyboard, because that's much easier, and an SD card, because we don't have to suffer from using floppy drives anymore, right? So let's put an SD card in there. And the design choice I've made is that this thing truly has no microcontroller to help you out. You have to do everything with your own designs, including updating the firmware, flashing the FPGAs themselves, and all of that. By the way, because I didn't want to be soldering the FPGA myself, I'm using these little boards called Broad by Magdin, and these are very nice boards also to get started. Yes, check it out as well. So there are two of them, one for the CPU, one for the GPU. And most importantly, it does run Doom, of course. And so here it's pulling the executable out of the SD card. This is a special port of Doom. It's a bit slow to load because I'm bitbanging the SD card. Just I thought it would be fast enough. And now you have recognized the normal Doom startup. Now something different happens. This is a CPU extracting all the textures and all the sprites and sending them over to the GPU so that the GPU can fill the texture memory. There will be sound. I hope it's not too loud. Yeah, and then the game is starting. Right now it's running on the CPU. So it's quite slow. The CPU is generating the frames and sending the frames to the GPU for display. The GPU does nothing. You can still see the performance is quite okay, given this is a full frame rendering at 25 megahertz. Right? When Doom was released, many of us were playing in small windows like that. So it's still sort of okay, but we have a trick. There is a new cheat code, and now I've enabled the GPU. And you can see that things are going to be much faster, and you can really play the game at full screen, even though it's only 25 megahertz. And here you can see, this is a demo recording that starts with the game. Yeah, sorry for the blood. You can see it's very snappy, so it's very dynamic. You can really enjoy playing. In fact, that's a problem because I spend more time playing than I should. All right, so modify Doom to use our custom GPU, check. Then there's another thing you can do, because of course this GPU has other capabilities, which are new. And what you can do is finally turn around, open this door, and explore the open world behind. And this is the Comanche terrain renderer. You can see it's fully integrated with the game, with correct Z-testing for the monsters. And you can walk around and try to escape this very nasty bug here. And you'll see at the end that we can go back inside to enjoy the level. So it's not as fast as I'd hoped. One reason is, this has been working since 4 days ago, maybe. And I didn't really have time to optimize the terrain distance or anything. Maybe I should add some volumetric fog to hide some of the details in the back. And the other thing is my memory controller is only 25 megabytes per second. I know it's possible to go 50 megabytes per second. One FPGA wizard, Sylvain Munot, managed to do that. So I will try as well, but it's very tricky. You have to manually place some of the logical elements onto the FPGA to be sure that it's at the maximum frequency. So I will try. So anyway, so this whole thing is a playground to do exactly the things I told you at the beginning, to exercise your performance mindset, to get back the freedom to hack, because that's your own hardware. You cannot break anything. You're free to pick and poke in memory and do whatever you want with it, and to experiment out of the box, because you can reconfigure these FPGAs. You can improve the CPU, the GPU, do whatever you want with it, having a very nice starting point already. So what's next for the project? Well, I already did quite a few steps. There's a custom OS. There's also a language like BASIC, but more modern, that you can code with when you start it up. And there's a V3 of the board. What I showed you was V2. The V3 is fully integrated. Unfortunately, I didn't receive it in time for the conference. It's being manufactured, and this takes a while. So definitely stay tuned if you're interested in the project. And yeah, come talk to me. I'm very happy to discuss about that. Thank you very much. There are many other designs in my repository. Everything I showed is available there, but for the computer, because I'm still working on it. And the GPU in particular is described in the repo at the bottom with a write-up on some parts of it. So yeah, thank you very much.
Thank you, Sylvain. And if you do want to tape out a bigger chip, I happen to work at Intel, right? So
yeah.
okay.
I'll keep that in mind.
All right, so we already have one. We will have time for a few questions before we go to the break, so let's go start it.
Thank you, Sylvain, for this terrific presentation.
Thanks.
This kind of like inspires me. Do you have any plans on building like a software abstraction for this, so that if you see how the world is changing? For example, if you look at cars, every button becomes a screen, and behind every button there's, so to say, a Vulkan chip behind it, but that just costs so much, and the application stays on that button for 10 years in the car. So what you could do is you could basically design a custom ASIC that would just do this one single application without the expensive full-blown Vulkan
yes.
GPU in it. Is something you thought about, like writing maybe a
Yeah,
graphics pipeline in software and then synthesizing directly a chip out of it? This would be like, if you sell 1 million cars, that
Yes.
would really pay off. I mean, this would be a giant business thing for you.
That's a very good point. And in fact, there are some initiatives. There's a framework called Litex, where you can, in a Python script, you can assemble hardware pieces, and it will generate the specific hardware and its firmware for it. The GPU I made is actually very simple to reuse. In fact, between the two designs, the single FPGA and the dual FPGA design, the hardware description of the core of the GPU hasn't changed at all. It's the same being reused. It's actually not very difficult to reuse pieces of hardware and plug them together if you have planned for it initially. There are even standard buses like AXI or this kind of things where people have agreed on ways to discuss between the different peripherals. So you can assemble your hardware and then get it implemented. Typically on FPGAs, this is great because it's just milliseconds, right? And so in the automotive industry, for instance, like in many other industries, FPGAs are very popular. The big advantage being that even if you did a mistake in your hardware, you can fix it, right? With ASIC, not so much. Yeah, no, I think some things are moving towards exactly what you're saying and having more reuse and being able to assemble hardware. Yeah, by the way, something that really puzzles me every time. Once you have done a CPU and you want a dual-core CPU, you just copy-paste your CPU instantiation a second time. And there you go, you have a dual-core, right? It's just so easy, right, once you have it. So, yeah.
Hello. I'm actually teaching kids how computers work, and with the kids we are designing 8-bit computers and simulations for them, but I'm using breadboards because that's the easiest way for me. But with the kids we pretty quickly get into topics like why we use resistors, capacitors, and stuff like that. And the topic quickly diverges to how electricity works and stuff like that. And I'm getting pretty distracted explaining these things. So do you have some advice about how we could focus our attention on the actual hardware and how it works instead of going to the electricity topics.
I see, I see. So you mean focusing on the digital part of it without being distracted by what's around? Well, I think really there are many different accessible FPGA boards that are made by the community. So I showed two of them, the Icebreaker and the Broad board. There was also the ULX3S at the beginning. These are all created for enthusiasts and people who want to learn about hardware design. And I think this is a great starting point because you have the board. The FPGA is completely empty at the start, and it's up to you to build it, but the rest around is already all done and all fine. So I think it's a good way to get started, focusing only on this part, and that's the way I did, and now I'm moving towards the PCB design and everything. But yeah, I think this way is guaranteeing that you can just work on the hardware itself and not get too much distracted by the surroundings, even though the surroundings are very important too, right? So I'm learning a few lessons along the way. So yeah, thanks. I think there were a lot of questions.
Thank you for the presentation. I really appreciate your passion on this whole project. For the last part of the presentation, you showed us the outdoor terrain, right? You mentioned it's not doesn't run as fast as you would hope to. Do you have any plans to optimize it? And if you do, like, how would you approach this? I doubt that you. Well, I think we are used to using Insight, but I doubt that works here.
Okay, thank you for the question. So yes, I do have plans. So first. So like I said, I think the main limiting factor, so I showed you that the texture data is in this external chip, right? And when it's a flash device, I can fetch a texel in 9 cycles. When it's a RAM device, it's 14 cycles because the delays are different. And this starts to be significantly slower, right? I can't really get around this, but by increasing the frequency of my memory controller. Right now it's running at 50 megahertz, even though the rest of the design is 25, so having these different frequencies is a bit tricky. I should run it at 100 megahertz. I've done that in the past, but the problem is you have to rely on the tool to minimize the delays in a way that will work for the design. And it's very tricky because at 100 megahertz, if it decides, if it's a bit less than the optimal placement, it's not gonna work, right? So the way I've seen people go around this is by manually placing parts of the design, specifying where some of the logics has to go on the chip, and I haven't tried that yet. But I know it's possible to double the speed of the memory controller, which would already go a long way. And then there are other things to optimize. I'm suspecting I'm rendering some of the things twice because the terrain has the floor has the terrain texture, the walls have the terrain texture. I'm not entirely sure I've figured out everything properly, so maybe I'm actually rendering some places twice, which would be bad, of course. I've got bitten by that in the past, so I'm suspecting this might be happening. And also there's the furthest distance for the terrain, which I haven't adjusted, and probably it's too much, right? It's tracing the ray too far away where we can't really see anything anymore. Thanks.
Right. So we have more time for questions in the breakout rooms because I was going to get to it. So just ambush Sylvain on site and let's thank him again.
Thank you.